So, we have compared various substations, the air insulated, the gas insulated and the hybrid type of substations. The equipments or the main components which are housed in any substations are of prime importance, and this maintenance of these components also are equally important. So, we will be seeing the main components which are housed in any air insulated or a gas insulated type of substation, the general principle of the operation of these equipments which are installed. The first component being the isolators, which are a very important component in any substation, mainly helps in the proper maintenance and the isolating of the circuit during the maintenance aspect. So, 132 kV and above will have a set of 3 individual poles which have a double braking arrangement with one vertical brake earthing blade per pole, that is very important, and these are suitable for fixing on either scale of the poles. So, these isolators similar to a circuit braking arrangement have earthing blades and have some short time current rating for their operation, and these are both thermal and could act as a dynamic short term current rating as that of the main blades. Interlocks are also provided to prevent the operation of isolator, particularly when the corresponding circuit breaker is on. So, the very important point, without interlocking facilities also been provided. So, these earth switches shall also be manually operated by a separate motor mechanism, operating mechanism for a typical which is being used in any substation for the isolation of the circuits connected with it. So, the operating mechanism shall be suitable, and it could hold the isolator either in a closed or in a open position wherever the requirement is there, and this will prevent the operation by gravity or by the wind or because of the short circuit forces, and could be because of the seismic forces. There could be wind or vibration shock and the accidental touching, etc. So, several of these aspects could influence the operating mechanism of isolator. The circuit breaker is a very important switching device, which is basically a mechanical switching device and capable of either making and carrying and breaking the currents under normal condition and also under specified abnormal conditions. So, types of circuit breakers which are in use for various voltage levels are 12 kV and 36 kV generally used, or minimum oil or bulk oil type, vacuum circuit breakers or ISF6 circuit breakers, sulfur hexafluoride insulation media. So, for more than 36 kV again minimum bulk oil, bulk oil or SF6 are available. For voltage levels of 145 kV and above, a minimum oil MCB or a minimum oil bulk oil or the air blast or the SF6 insulating breakers are generally used in any substation. Similarly, for 220 kV and above, 420 and above, either minimum oil or a bulk oil type, air blast or SF6, these 4 types of circuit breakers are generally used for higher the voltages. However, both the minimum oil, the bulk oil and the air blast are phased out with the advancement of technology. So, the recent advancement because of the SF6 technology and having better insulating properties compared to the earlier oil type of or minimum oil type of breakers. So, voltage levels above 145 kV and above employ SF6 breakers, and vacuum circuit breakers are generally used for 11 and 33 kV or lower voltage levels. So, these circuit breakers may be of live tank or a dead tank design. So, live tank breakers are generally used for outdoor substations which have an interrupters housed in a porcelain weathering shields. So, the circuit breakers pertaining to the dead tank type have interrupters housed in an earthed metallic container with their connections which are normally brought out through the porcelain bushings, and these bushings may be used to house the current transformers. So, this is the use of the porcelain housings for the circuit breakers, either if it is a dead tank or it is of the live tank arrangement. So, these circuit breakers are very important component as said, and are most critical switching elements in a power system, and circuit breakers are only a means of interrupting fault currents in the extra high voltage or ultra high voltage system, a very important component. So, we will just focus about the importance of the circuit breakers, the type of circuit breakers which are used in the EHV and UHV substations. The circuit breakers are very fast, and secure fault interruption is required not only for the protection of transmission system equipment, but also for overall operational system stability is the utmost important point. The interrupted rated current under no load and the loaded condition, and also under the fault conditions up to rated symmetrical fault currents, it should be able to operate. Circuit breakers are placed on variably considerable with nature of circuit involving the being switched to the required time, and interruption of fault currents at very high voltage levels could lead to high thermal and dielectric stress on this breaker. So, this has to be considered before going in for the proper design of the requirement of the breaker. So, even low level fault currents which are of capacitive or inductive in nature can also place very high stresses on the equipment that is on the circuit breaker. So, what are the main important functions or the circuit breaker has to perform are classified as follows. So, the circuit breaker should primarily focus into the 4 important functions. It should carry the rated current at the rated voltage, a very important point. It should carry the rated current at rated voltage, and power frequency, whatever the power frequency voltage which it is intended to operate continuously when in closed position. So, when the circuit breaker is closed, it should be able to carry the rated current of the bus bar or the rated voltage which is to be operated, and the power frequency 50 hertz or which is designed in the closed position, and it should interrupt the rated current at the rated voltage and power frequency on trip command. So, once the command pertaining to the opening of the circuit breaker is given, it should be able to interrupt at that supply current or rated current which it is being operated. So, these interrupt fault current in case of fault in the transmission system, also interrupt line charging currents and induction currents. So, it should be able to interrupt any fault currents which are generated because of the transmission system. And the final point to be seen is it has to maintain the rated dielectrics, that is the insulation properties, both for the power frequency and the impulse or the surge withstand levels when it is in open position. So, the insulation properties of the circuit breaker are also equally important for power frequency and surges which it withstand during the opening of the circuit breaker. The transient recovery voltage is a very important term in the characteristics in the circuit breaker. So, voltage which appears across the terminals of the current interruption. So, the characteristics of the transient recovery voltage, that is both the amplitude and the rate of rise, this could lead to either successful current interruption or to the failure because of a restrike or reignition, So, for successful current interruption, there should be neither reignition nor a restrike. So, this has to be done so that the characteristics have to be successfully quenched without the reignition or the restrike. So, the transient recovery voltage waveform is generally represented by the two parameters which are seen here, the current waveform which is indicated in the here, and the transient recovery voltage waveform. You can see the transient and the recovery voltage, the supply voltage is somewhere here which is the dotted line, and this is the transient recovery voltage over a period of time. So, very important, it should be able to see the successfully interrupts the restrike or the reignition which has happened. So, how to select the rating of a circuit breaker is again an important planning which has to be carried out by the substation designers for various voltage levels. So, some of the typical technical details are given here as per the international standards which are available. You can see the rated voltage levels from a very low 36 kV to the 800 kV voltage levels. The requirement for the circuit breaker, the rated short circuit breaking capability or the current in terms of kiloamps. For a 36 kV, it should be able to break the current at 25 and 31.5 kiloamps. As the voltage level increases, you can see for a 800 kV or EHV, that is a 420 and above, the rated short circuit breaking current should be able to break 40 to 63 amps kiloamps, sorry, and for 800 rated voltage, minimum of 40 kiloamps should be the rated short circuit breaking capability of circuit breaker. And the normal rated current in terms of amperes, you can see for 800 kV system, the normal rated normal current could be anywhere between 2000 3150 amps. For a voltage depends, for a lesser voltage it could be 1600 amps, the rated normal current which it sees. So, the total break time as per the international standard, that is 62271, clearly mentions about in case 145 kV voltage level, the circuit breaker should be able to operate within 60 milliseconds to 100 milliseconds, and in case of 245 kV, the total break time which is mentioned as per standard should not exceed more than 60 milliseconds, and for EHV transmission substation or EHV transmission levels more than 420 kV, it should not exceed 40 milliseconds, and for 800 kV it should not exceed 40 milliseconds. So, these are the total break time as per the international commission which has been specified for the selection of the circuit breaker ratings. So, this is a typical example of how a high voltage or extra high voltage circuit breaker looks. You can see it has to perform various functions as mentioned earlier, such a huge equipment which is to be in the circuit, and it has to properly function either in making or the breaking of the circuit whenever it is required. So, this again is one of the typical example for the extra high voltage circuit breaker which is being employed for a very high voltage or ultra high voltage levels. Further, with the development of the SF6 technology, sulfur hexafluoride insulating media is used as a insulating property. So, here again design of the circuit breakers with SF6 technology has gained importance in the recent years, and several of the breakers with SF6 technology are being employed for the higher the voltage EHV and UHV transmission levels, consisting of both the interrupting units with several interrupting units connected in series, which is an advantage, and also high speed switch for closing the resistors. So, several options are been available and designs are available from various manufacturers across the globe. So, the weight of the circuit breaker is also drastically reduced by going in for SF6 technology. So, for 1100 kV various type of circuit breaker from different voltage levels are just highlighted here. You can see for a 300 kV with single interrupter, for 550 kV with 2 interrupters, and 550 kV with PIR. What is PIR is very important, pre-insertion resistors. So, why these pre-insertion resistors are used for circuit breaker, we will discuss about this. And this circuit breaker again is used for 1100 kV with the PIR. So, the technology has advanced, and the compactness of the breaker has also been achieved by going in with the SF6 technology. So, this PIR pre-insertion resistor is a very important which is being used in the circuit breakers. Generally it is 200 to 400 ohms, and which this gets temporarily closed before closing the circuit breaker. The sequence is operation of the circuit breaker is the closing of the pre-insertion resistor. After closing of the pre-insertion resistor with a gap of 10 to 12 milliseconds, the closing of the main circuit takes place, circuit breaker contact takes place. So, this is the important function. How it is important? See, while again in opening, the pre-insertion resistor is first disconnected by the breaker operating mechanism, and after 10 milliseconds the main contact of the breaker are generally opened. So, this is the mechanism of the use of the pre-insertion resistor in the circuit breaker. The main purpose, the main important purpose of using the pre-insertion resistor is to limit the initial charging current of the transmission line. So, as the charging current of long line will be much more, so it is advisable to use the breaker with a pre-insertion resistor. So, few of the examples are shown here for the very high voltage with for 550 kV with the pre-insertion resistors, similarly for 1100 kV. So, the PIR serves to limit the initial charging current of a long line, and it is advisable to use the breaker for better protection above EHV levels with the PIR inserted in the breaker. So, that was about some of the important components which are in the substation. Continuing that, insulation coordination is a very important aspect for the proper design of the substation or the transmission or any of the equipment, electrical equipment which is being used for the very high voltage levels. So, the electrical equipment, we know that insulation or dielectrics must be specified, designed and constructed in an optimized way. This we have tried to discuss in the comparison, and the main intention of going in for insulation withstand not only to see that it has to be in optimized way, and also to see that it withstands the electrical stresses for a long period of time which can be expected in the electrical network. The main goal is also to see that it is essential for the reliable operation of any electrical system, and this has to be achieved by applying the principles and practices of insulation coordination. As the voltage level goes higher and higher at extra high voltage and ultra high voltage, the planning of insulation coordination gains a very important or is considered to be an important aspect for a very high voltage levels. So, the insulation coordination is in fact the methodology which will help to ascertain the electrical stress that could occur in any electrical network, and this will coordinate with the stress with the withstand characteristics of the electrical equipment in a techno-economic manner. That is very important point to be considered, techno-economic manner. So, it should be also economical, it should be technically viable, so that the result in selection of the insulation level that is optimized from a reliability and an economic perspective. So, the insulation coordination plays a very vital role above 400 kV or EHV or UHV transmission substation or insulation aspect. So, various voltage stresses in service we have discussed earlier. The main is the system voltage and the over voltages. Again, the over voltages are categorized into temporary over voltages, which could be for a few cycles, a few tens of milliseconds, and light switching surges. Again, it switching could be of the operation of the circuit breakers, closing and opening of the circuit breakers or any other switching activity. And lightning is mainly caused by the natural lightning, the lightning surges which impinge on the transmission or the distribution network could create the voltage stresses in the insulation of the equipment in service. So, these over voltages in any network, when you look into this graph which shows the amplitude, that is the voltage amplitude in per unit of the peak value, is the y axis, and x axis is shown as the voltage duration, that is a time period in seconds. You can see here for the lightning aspects, in case of the lightning, the surges which are developed because of the lightning activity could be a very fast fronted type of over voltage surges. So, earlier we have discussed, so lightning over voltages could be of the fast fronted nature, that is a very steep fronted, could be of in microseconds, that is 1.2 microseconds could be the front and the tail could be anywhere between 50 microseconds. So, these lightning surges could be of very high magnitude and fast fronted. The second surges are of switching in nature, the switching again because of the closing or the opening of the circuit breakers. These switching surges are comparatively slow fronted surges or over voltages. This slow front again it could be 250 milliseconds, there it is a microseconds, 1.2 microseconds, it is 250 milliseconds, microseconds and 2500 microseconds. So, the surges of switching have a typical wave shape of 250 by 2500 microseconds. Apart from lightning and switching surges, we have a temporary over voltages which could last for few cycles. These again are of low frequency, could be of the power frequency related over voltages slightly above the normal operating voltages. And finally, the entire power frequency voltages which are in continuous in nature, where the electrical stress on the insulation lies, this will be for a longer period of time. So, this gives the clear differentiation between various surges or the transients over voltages like switching lightning, and temporary over voltages which are of low frequency, and the power frequency which could be for a very long period of time. These are various over voltages which occur in a transmission or a distribution network. So, how the strength of a typical insulation is estimated? You can see here this graph gives the voltage amplitude per unit of peak value again versus the voltage duration. This gives you the basic insulation level in case of the lightning impulse withstand of the equipment, or the switching impulse or switching surge withstand impulse level, including the surge impedance loading of any equipment. So, the power frequency withstand is given for the voltage amplitude which is shown as per unit. So, you can see the basic lightning impulse withstand level could be any way between 4 per unit, but the basic insulation level is 2.8 to 3 per less than 2.8 per unit. For switching impulse or switching surges withstand, it could be 3.5 with surge impedance loading, and lesser than that it could be 2 to 2.2 per unit. And for power frequency it could be around 2 per unit of the peak value, where this surges or the typical insulation strength of the equipment is considered. What are the insulation levels and the clearances? These also have been discussed earlier. So, insulation levels and clearances are very important, and this will be based on the proper design or insulation coordination studies which are to be conducted. A typical example for one particular substation in the country, that is a Sioni substation of 765 kV is given here, how the parameters have been identified and how the insulation coordination has been done for the actual system of 765 kV substation. Very clearly you can see electrical clearances which are designed, the main parameters and the value are given here. The electrical clearances from face to earth, that is the conductor to the structure, the required coordinated value is 4900 millimeter. For face to earth, that is a rod to structure, it is 6400 millimeter. Face to face, that is a conductor to conductor clearances is 7600 mm for a 765 kV substation, and the face to face conductor to rod, it is given estimated to be 9400 mm. And the circuit breaker requirements, that is the insulation level requirements for a circuit breaker. The lightning impulse withstand level LIWL is 2100 kV. Switching impulse withstand level is 1550 kilovolts. For the transformer and the shunt reactor, the insulation level required for a 765 kV substation is lightning impulse withstand level is 1950 kV, and for switching impulse withstand level is 1550 kilovolts. So, some of the practical information which is being used in the country for a 765 kV ultra high voltage substation. These are some of the clearances for transformer, circuit breaker and the shunt reactor, and the values prescribed based on the insulation level and the clearances required. Similarly, insulation levels for a very high ultra high voltage systems, a comparison is generally done here. You can see for equipment which are used at 1100 kV test station in Japan, and the equipment which is in service in China, and the equipment under construction in India is been given here. You can see the first row corresponds to the equipment under test at Japan for 1100, the power grid in India for the values of 1200 kV, and in China 1100 kV. A comparison has been made. You can see the lightning impulse withstand values, the rated voltages are being 1100 in case of Japan, 1200 in case of India, and 1100 in case of China. The lightning impulse withstand voltage level for a circuit breaker in case of Japan 1100 kV, the requirement has been estimated to be 2250 kilovolts. In India for 1200 kV it is 2400 kilovolts, and a similar voltage level 1100 for in China it is followed 2400 kilovolts. For transformer it is 1950 in case of the comparison in Japan 1100 kV system, it is 2250 both in China and India for 1200 and 1100 kV respectively. It is about the lightning impulse withstand. For switching impulse withstand for the circuit breaker and the transformer, the values are given here. You can see both for 1200 kV and 1100 kV the values are identical, that is 1800 kilovolts both for circuit breaker and the transformer are being estimated and being planned to be used in the substation for ultra high voltage substation. So, comparison of the insulation levels for different system voltages are given here based on the estimation. So, you can see here various voltage levels from voltage levels of 220 kV to the EHV level ultra high voltage levels 800 and 1200 kV. The rated voltage peak 1 per unit per kV is very clearly given here. For 240 it is 200, for 420 kV it is 343, 800 it is 653, and for 1200 it is 980 kilovolts. So, 1 minute power frequency withstand voltage for this insulating system for a 245 kV the requirement is 460 kilovolts, and for 400 it is 630, 800 kV it is 960, and for 1200 it is 1200 kV. So, it has to withstand for 1 minute operating voltage power frequency withstand. Then switching impulse withstand, Lightning impulse withstand values are also given here. For 220 kV system, the lightning impulse will be 1050, and for 400 kV it is 1050 in case of switching and 1425 in case of lightning impulse. For 800 it is 1550, 2100 kV, and for 1200 it is 1800 and 2400 kV is the specified limits for the lightning and switching impulse voltages. In case of per unit, this gives the values for switching impulse voltage, lightning impulse and lightning impulse withstand level for rated voltage. These are the per unit values which are being given. You can see for a 420 kV it is 3.06 and for 1200 it is 1.86, and in case of 800 it is 2.3 for switching impulse, and for lightning impulse it is 4.15, 3.22 and 2.45. This is a very important aspect to be considered for the various insulation levels. This gives an idea of the insulation coordination which is being done for the various voltage levels which are being adopted. So, the important component of the substation is the surge arrestor, which is plays a major role to control or to contain the over voltages which have been discussed. It could be lightning, it could be switching or other over voltages. So, surge arrestor plays a major role, and proper planning coordination of this is very important. The parameters of various equipment are decided considering the presence of this surge arrestor in the system, and these surge arrestors are connected to each phase and ground. So, the system to control the voltage trace that these equipments will experience under normal and also any contingency conditions. So, the surge arrestors require very high energy discharge capability, very important. As the voltage level goes, the current carrying capability, the power requirement will be high. So, the substation which the surge arrestors are housed have to see the energy discharge capability. So, very important. So, again the energy it could be a distribution, it could be a class 1, 2, 3, 4, 5. So, various class of surge arrestors are being used for different voltage levels to see the energy which is discharged, and the surge arrestor should be capable of discharging the surges to the ground to see the equipment is being properly protected. So, the discharge capability is considered with the stringent duties and sustained over voltages, particularly in the ultra high voltage system and extra high voltage systems. So, a single phase to earth fault gives rise to over voltages in healthy phases up to 1.4 per unit. So, the fault is generally cleared in 100 to 140 milliseconds by opening local end circuit breaker at 120 milliseconds and the remote end of the circuit breaker at 140 milliseconds. So, the energy which is to be handled is very important. The energy which is to be handled by metal oxide surge arrestor during these conditions, during the fault clearance conditions, or the fault is to be cleared with the opening and closing conditions, such a huge energy is to be handled by this metal oxide surge arrestors, and due to the temporary over voltages could be about 35 megajoules. So, high energy up to 35 megajoules. So, the above duty followed by the discharge class, that is the class 5 of the surge arrestors, where 2 shots of 5 megajoules each, and a margin for non-uniformity accounts usually for about 55 megajoules for metal oxide surge arrestors are used for such a high discharge class. So, when we look into the VI characteristics, the volt current characteristics of any typical surge arrestor, the y axis shows the kilovolt per peak in magnitude, and the current kiloamps in x axis. You can see the characteristics of the surge arrestor is typically looks like this, where initially rises and tries to stabilize at a current rating after say 8 kiloamps, and you can see that the stability is maintained. What are the surge arrestor parameters? The surge arrestor rating, in case if it is 850 kV RMS, the continuous operating voltage of the arrestor will be 693 kV. So, for a rating of 850 kilovolts, the continuous operating voltage of a surge arrestor will be 693 kilovolt RMS. The minimum continuous operating voltage MCOV of arrestor is 723 kilovolts, and lightning impulse protection level at 20 kiloamps is 1700 kilovolts per peak, and switching impulse protection level at 2 kiloamps is 1500 kilovolts per peak. The energy of the arrestor which is to be diverted will be 55 megajoules, and the pressure relief class is 40 kiloamps. The line discharge class is class 5 as per the International Electrotechnical Commission. So, these technical parameters are for UHV ultra high voltage range more than 765 kV level protection system which is being used in the substation. So, or higher, that 1100 kV or 1200 kV systems. So, similarly some of the technical requirements of the metal oxide gapless arrestors. Again, arrestors are basically classified into gapped and gapless. I would like to mention here the old technology, the technology which was earlier used was a gap type of arrestor containing the silicon carbide elements stacked one above the other with gaps in between each blocks. The recent technology is using the metal oxide zinc oxide based arrestor elements which are stacked one above the other without a gap. So, that is the reason it is known as a gapless type of arrestors, which is a recent technology being used for the extra high voltage and ultra high voltage transmission system. So, this table gives information about various voltage levels of the arrestor which is being used. Rated arrestor voltage 320, 216, 120, 33 kV class, and the maximum continuous operating voltage level is given here. And typically the installation is outdoor. A class could be heavy duty station class, that is a gapless type of arrestors are employed. So, type of construction for 10 kiloamps rated arrestor, it should be single column, it will be a single column. If the voltage level goes higher and higher, the surge arrestors have to be in parallelly connected and going for 2 or multiple columns, and normal discharge current corresponding to the lightning impulse of the surge arrestor at 8 by 20 microsecond wave shape will generally be a 10 kiloamp RMS for all the type. The type of mounting will be pedestal. These are some of the technical aspects of the lightning arrestors which are used for lower voltage class less than 400 kV, and the long duration class is class 3, there are class 2, 3 and 4 and 5. So, ratio of switching impulses, these are some of the technical parameters for switching, and symmetrical fault current in case of pressure relief has to be operated. So, these are the values 40 kiloamps RMS. And the corona extension, it depends on the rated voltage of the arrestor. The corona extension voltage has to be defined by the rating of the arrestor. And what is the maximum interference, radio interference with the energized minimum continuous operating voltage, it should not exceed 1000 microvolts or 500 microvolts if the voltage is very less. And the minimum creepage distance of the arrestor housing requirement, again it depends on the voltage level here. This is the creepage length which has been technically given. So, this shows the typical surge arrestor which is being used for a EHV or UHV transmission. The column of the ceramic bushings containing the number of elements in blocks, zinc oxide blocks which are housed in this ceramic housing. A similar surge arrestor is shown here. So, these are typical examples which are used for the EHV and UHV transmission systems. Again this figure shows the surge arrestor or zinc oxide blocks. These are the zinc oxide blocks which are stacked inside the porcelain housing with suitable pressure relief arrangement and pressure valves in case of emergency. So, this is how the blocks are rated for various classes from the distribution class 1, class 2, class 3, 4 or 5, which are being used for ultra high voltage systems. A very important component, and the insulation coordination is mainly to see that the equipment like the transformer, the switch gears are protected. So, surge arrestor plays a very important role in the substation for the coordination of the insulation. This is one of the example which a first prototype of 850 kV surge arrestor which is being used for 1200 kV system is shown here. It consists of a multiple stacks, 4 stacks, parallel stacks combined with several zinc oxide elements housed in this ceramic shells. So, this is one of the first type of design when required for a 1200 kV experimental line in the country was developed. Some information about the parameters and some arrestor details based on the values, how the rating of the element is calculated. The information is available in the standards pertaining to the surge arrestors. But anyhow I would like to give some information on how the number of blocks are chosen for a particular rating. So, you can see here depending upon the discs, number of discs, in case it is used for the discharge class 5, the rating of the disc continuous the rating of the disc could each be 3.3 kilovolts. So, in case of the 3 point rating of the zinc oxide element, that is a block, is 3.3 kV RMS used for 20 kilo amp level and the discharge class is 5. So, how many blocks in one column? It is estimated that 850 kV is the voltage level divided by the 3.3 will give 258 arrestor blocks to be used. So, the residual voltage or the protection level, lightning impulse protection level with considering 4 parallel columns at 20 kilo amps is 5 kilo amps per column. So, it comes down to, as 4 columns are there. So, 258 blocks into 6.65 kilovolts will give you 1715.7 kV peak is the total residue voltage of the surge arrestor of 850 kV rating. So, similarly residual voltage protection level for switching impulse with 4 columns comes to 1496 kilovolts. Again this is calculated based on the number of blocks and the voltage level, switching voltage level of one single arrestor. So, it comes to 1496 kV. Then the minimum continuous operating voltage of the arrestor is 2.84, it is a 3.3 kV disc. So, 2.84 is the minimum continuous operating into 258 blocks will give you 732 kV RMS. The energy handling capability for 4 columns as shown here, these 4 columns will be the operating duty test into number of discs into number of columns. This will be typically 55.78 megajoules which is very high. So, the energy in long duration withstand test, again it depends on number of discs into number of columns, say 54 kilojoules and 258 into 4, it is 55 megajoules of energy has to be handled by the arrestor elements. So, this is again the matching of electrical characteristics which are used for 1200 kV system. Operating voltage is 850 kV for a voltage current rating of 20 kilo amps and discharge class as mentioned earlier class 5. So, the maximum system voltage is 1200 kilovolts. The rating of arrestor which is already decided is 850, that is 71% of the maximum voltage which is operated at 20 kilo amps discharge class. So, maximum continuous operating voltage will be 1200 by root 3 693 kilovolts. The desired minimum continuous operating is 725 727 kilo volt RMS. So, the tested value of the minimum continuous operating of arrestor both for duty class and for transient conditions is 727. So, the equipment which is tested is lightning impulse withstand and switching impulse withstand voltage levels is 2200 and 1800 kV respectively. And in case of programmed case, lightning impulse protection level is 1725 and switching is 1500 kV, but actual it is 1715 and 1496. So, the protective margin is higher for both lightning impulse and switching impulse. So, other details of estimation like the total creepage distance of the entire arrestor housing is 32,300 mm, which actual requirement is 32,800. So, height from the mounting plane is 9,700 mm and dry arcing distance 8,150 mm. The grading ring to arrestor bottom and the routine bending load specified long term load is 6 kilonewton. So, these are some of the technical parameters which are required to be estimated for the 1200 kV lightning arrestor which is being housed in the substation. Thank you, we will continue.